Hello, welcome to day 18 of the Advent of Code Challenge. So today's stream is going to be a little bit different. I started recording this last night as I was trying to do it. In the end, it took me probably about an hour and a half to complete this challenge. And I thought probably wouldn't make such a nice video to watch me struggle through this for an hour and a half. And so what I've done is I have completed it, and now I'm going to go back and explain my solution for this video today. So the format is going to be a little bit different because I already know what I'm doing, and I'll just be explaining the process I went through to do it. If you look at the leaderboards, you'll see that this challenge was particularly hard for a lot of people. I did it probably, like 6 hours after it released, and less than half the people from yesterday, from the day before, managed to do this puzzle at that point in time. It was definitely a very tricky puzzle. You had to know your data structures, and you had to know some ways of traversing those data structures in order to be able to come up with a solution. And so, I'm going to walk us through that. And so I'm going to assume that you have read the description because it is a very long description. It would probably take me 10 minutes just to read that out loud. If you haven't read it, you can pause the video and go take a look. Ultimately, it's not that hard. It's just very wordy, and there's a lot of different ideas and concepts that you have to go through in order to get to the answer. And so the general idea is that there are these numbers that are written in pairs, and then there are certain operations that you can do on them and how they behave. And at the end, you have to take your input. And do this addition operation, which they define on these pairs of numbers, all the way until you find this magnitude. So a lot of things to go through. I think the first thing is how you represent these numbers in memory is probably one of the most important things. For me, what I chose, so when I first looked at this, I thought it looked a little bit lispy, some kind of cons list, but or maybe a list of tuple twos. But I decided that wasn't with what I could do in Go. I decided that wasn't really the best way for me to approach it. So in the end, I decided to use some kind of tree structure, because you know that these are pairs. So this kind of fits well into a binary tree structure, and that's what I did. And so the first thing I think for us to do is to be able to parse these things into an in-memory data structure. So what I did was I defined two types. The first type was a type strip pair, which has a left and a right. Now, in a language with better types, such as Scala or Rust, Haskell, that sort of thing, you could put a better type in here. And Go, unfortunately, has to be interface. Because the second type that you could put in here is a num, and that has a value, which is an int. And so what I'm saying is that I'm going to represent these pairs as pairs, and each thing, so for example, this 1, 2 is going to be a data structure that looks like this, like that. That's the general gist of what I'm doing. And then, for example, the second data structure here, what I want is I want this to be this sort of thing, right? And I hope that makes sense. And so what I want to do is to be able to take these things and parse it into this input. Now, a couple of interesting things I noticed when I looked through my input is that every number is from 0 to 9. There are no two-digit numbers in here. And that makes parsing this extremely easy because there's no spaces, there are no two-digit numbers. So what that means is you can look at you can look at the input strings one character at a time in order to parse it. And so I'll be copying code back and forth between my solution and what I'm working on here. so I don't have to type it out. And so to parse it, what I did was I first created this helper type that I called a stream. And the stream, I called it a stream. I'm not sure what you're supposed to call it. And what all this does is it lets me save the state of, it's an object that lets me save the state of where I am up to in my string. That's all it is. So to create a new stream, I'm going to call it, make a function called new stream, like this, and it just returns the string inside it, and I, which is my position, I could call it pos, which starts off at 0. What I then want to do is have a function that modifies this, and I called it next. And all it does is it returns the next character, and this is a mutating function, so every time you call next, you're going to get a different result. So all it does is it goes, the string is that you want to return is going to be s.s indexed at position, whatever position I'm at, as a string. I'm going to increment the position, and I'm going to return that character. And that's all it does. So that's how the stream works. Now parsing it, right, there's a couple more things in here that I didn't show. To make this work well, especially because so the first thing is in tree structures, you kind of always want to be able to refer back to the parent, because then you can go up the tree. And so that's the first extra parameter that goes into both of these types. And the second parameter that I decided for me to keep track of, which made my life easier when I'm doing the actual operations on the data structure, is to just keep track of the depth of my of this specific pair, like node, or this specific leaf, the number. Because this meant that there were certain operations that I didn't have to keep counting up. You can get the depth by counting the number of parents you have above you, for example. But I didn't want to have to do that, and so I decided to just write the depth into my structs. Now there are certain dangers with doing this, because as soon as that gets out of sync, you're going to run into trouble. And I did actually run into a couple of bugs that way. But for the purposes of this specific puzzle, it was good for me to be able to keep track of that. And so that's what I did. And so that's why this parse value function takes in both a parent, and a depth. And so what I did was I had a helper function called new pair, which takes in that string. So this might be, for example, a string like this, and it returns a pair, which is the decoded structure. And what this would return is it would return well, one of the other things is in this specific challenge, none of these values are ever going to be a regular number by itself. It's always going to at least be a pair. And so, okay, we'll come back to that. What we want to do here is to parse this. There are a couple of ways to parse, two things we're looking for. The first thing we're looking for is at every point when we have a value, it is either going to be a number, it's going to be a one-digit number, or it's going to be an open square bracket. Now, if it's an open square bracket, it's going to be the start of a pair. And if it is a number, it's going to be a value. Those are the only two possibilities when reading, when decoding one of these strings. Now you might ask what happens to the comma or the closed square bracket. Well, those fall into the category of the open square bracket. And so the open square bracket here deals with when the value we're reading is a pair, and the default deals with the value when it is a number. And those are the only two cases. Now, when you read a number, this is probably the easier case to understand, so we'll start here. When you read a number, because we know that these are all single-digit numbers, we've read one character next. So we know if we know it's a number, we convert it to a string like this. I ignored the error. Yes, I ignored the error. And then I just return a new number struct, which has the parent, the depth, as they are passed in the function here, which we'll get to in a bit, and the value. That's all it is. Now, parsing a pair becomes a little bit trickier. And this is where your ability to understand and use recursive functions becomes really important, because this entire puzzle is based on this recursive data type of a binary tree. And so all these functions that we're going to look at today are in some way recursive. To parse a pair, first we read the open square bracket. We've read it, that's good. Now we don't care about the open square bracket. We create a pair first with the parent and the depth as passed into the function. And then the next character we read is going to be the next value. Now that value could either be a number or a pair, but we don't care which one. We just care about the next value. And we say, so all we have to do is call recursively parse value again. Pass in the same stream, which has been advanced a character, which is why I wanted to have that string in a struct. The parent is going to be this new pair. See, this P is this new function, the pair that we just created, and then the depth has increased by 1, which hopefully makes sense. So once we've parsed the next value, recursively, whatever that is, this is either going to return back a pair or a number. We skip the comma, we pass the right-hand value, we skip the close bracket, and we have parsed a pair. And so this is a really nice, succinct, concise way to parse, to recursively parse a pair. A pair. And so to do this, so to wrap it up into something that's a bit nicer, we can just pass in the string and not worry about parents and things like that. This will be parse value. We need a new stream of the S input string. The root parent is going to be nil, and the root depth is going to be 0. Now we can't just return this because it will complain that this returns an interface, as you can see. Now it has to return an interface because it can either return a pair or a number. We don't know which one. But here we know for sure that it's going to be a pair just because of the constraints of the puzzle. But Go doesn't like that. And so there are a couple of ways to do this. But the way that came to me off the top of my head yesterday was I just did this, and then I said, and I just did a type switch. Cool. And then you have to have a default case because otherwise the compiler doesn't like it. So I just said panic with the the string, so that we can see what the error was. So let's take a look at that function. If we go new pair, and then this is going to be data 0, you will see that we've parsed it into this. It prints it out. Now this is a little hard to read because if we print it with the field names, it might be a little bit more understandable. Okay, so we have the parent is nil, the depth is 0, and then the left and right are pointers, and that makes it a little bit harder to read, especially when we want to debug it. And so what I did was I used the string function. If a type has a string function, a function called string, then it implements the interface stringer, and when you print if it uses whatever the output of this is instead of the default struct thing. And so what I did was I said, if I'm printing a pair, I want to print out. Okay, I'm just going to copy this because I'll just copy both of these because I don't have to type it out again. I have two different versions here. One that I use for debugging, but we won't use the debug version. The debug version shows me the depth of it as well, and because I ran into some problems with depth, But if we want something pretty printed, to print out a pair, you just print out the square brackets, the comma, and then the left and the right values. And for a number, you just print out the number. So this could actually be like A to I to A, instead of printf. But yeah, it is what it is. And so now with these string functions, we get nice output, as you can see in the bottom half of my screen. Yep, so we can just check that this works with all the other types. You can see that that parses properly. In fact, oops. Let's just take a look that these all parse properly. And you can see that they all look exactly like the input, which means they parse correctly. So that was the first step, was actually getting these things into a structure in memory that you could represent and could traverse and could do stuff with. Now the next part of the puzzle is said it's this addition operation. Now the addition operation is quite straightforward. It just takes two of these pair numbers and it sticks them into a new pair, right? One on the left, one on the right. So to do that, we simply have to add them together, create a new pair. And this particular function should look pretty straightforward. I'm just going to pop it in here because then it's a little bit easier to reference. So there's quite a lot of extra stuff in here that we're not going to look at yet. But at the highest level, adding two pairs, A and B, is you create a new pair. That new pair is going to be the top pair, right? The root, because it's right at the top. And so the parent of that new pair is nil, the depth is 0, and then you have your A and your B, which are your two pairs. Now your A and B used to be root pairs, I guess. It's the easiest way to talk about it. And so you need to change the parent. And so that parent, both of them need to point to this new pair as the parent, right? Which makes sense. And the other thing we need to do, because I'm keeping track of the depth, I need to increase the depth of every pair and number in those trees. And so that's what these two function calls do. Now, increasing the depth is quite straightforward. So you can see, to increase the depth of the pair, you increase the depth of the current pair. And then for the left and for the right, if it's a pair, you recursively call inc depth on it. But if it's a number, you just add the depth on the number. And that's it. Do the same thing with the one on the right side. And so this idea is going to show up a lot. For the left side and the right side, depending on whether it's a number or a pair, you do something slightly different. Usually with the pair, it involves recursively calling the function on yourself. And if it's a number, because it's the leaf node, you are done and you just do your final thing. So hopefully that function makes sense. So that's just resetting the depth on all the tree, on everything in the tree. So you will see, for example, if we use this example that they give, what's the best way to do this? A is going to be a new pair. This, B is going to be a new pair of this, and we are going to print A, B, and then add A and B. Let's get rid of that unused warning. So we have A, which is 1, 2, B, which is 3, 4, 5, and then added together is, as you can see, what they say it should be. Now, the next step to adding, though, is, of course, reducing. And this was the hardest part, I think, of the challenge. Two different scenarios. One is what they call exploding, and one is what they call splitting. Now, I racked my heads around how to do heads. Did I say heads? My head around how to do this because it's not easy to traversing a tree while it's logical and it makes sense. The code ends up being quite hard. So what I did in the end was I did some kind of iterator-like thing. what I noticed was that, excuse me, I've got to blow my nose. What I realized was that with the explode function, what I noticed was that it's always the number on your left and the number on your right. You don't care about all the brackets in between, right? So with this, for example, the 2 and the 1 go together to become the 3. 3 and the 4 go together to become the 7. And then this entire pair becomes a 0. And what that means is if only there was an easy way to be able to iterate over the numbers directly. And it turns out there is. There are 3 different main ways to traverse a tree structure, and I can't remember the exact names for them, but it's pre something, in something, and post, right? Pre, in, and post. And this is basically a post, an in, I want to say infix, but I'm not sure that's the right word, but it's that kind of traversal. To traverse it, you basically, at every node, you do the left branch, you do yourself, and you do the right branch, or the other way around because your camera's the other way around. Now with a language like JavaScript or Python, which has generators, this is really easy to write in a efficient way. With Go, I don't know if there are generators. At least I don't know that you can. Maybe you can, but I didn't know how to do it. And so I decided in the end to just create an entire array of pointers, and I'll show you what that means. Right, so it's probably easiest to just look at the function, and then we'll work our way from there. I called the function iter. It's not technically an iterator, but it will have to do. So I just pop it in here. So what this function does is I build an array of nums. So I build an array of all my leaf nodes. So it will traverse the tree and pull out every leaf node from left to right. So no matter what the structure is as a tree, and I have all these trees drawn on my piece of paper when I was working it out, no matter the structure of the tree, what this function will do is it will flatten that into an array where each successive element in the array is going to be each successive number in this thing. So for example, if I plug this in, it will give me 9, 8, 1, 2, 3, 4. If I plug this in, it will give me 7, 6, 5, 4, 3, 2, and so on. And the way I do that is it's almost the same as that ink depth function we had earlier. When we give it a pair, it will first look at, it will, you create an array to hold the final result. You look at the left side of your current pair. If it's a number, you append itself to it. If it's a pair, you append iter of itself to it. So you recursively call it, and then you do the same with the right-hand side. And this will flatten out the entire tree. So let me just demonstrate what that looks like. If I have A, this should be quite straightforward, and it should make sense. That I have, you can see there's no comma here because this is an array. But when you have a more complicated structure like this B, you see it's flattened out to 3, 4, and 5. And these are the pointers to those structs. So if we give it something complicated like this, even, you see over here, it's flattened it out to just 6, 5, 4, 3, 2, 1. And if that doesn't make sense to you how that works, it is a good opportunity to look up tree traversal methods, because this is what that is doing. But because I've done this, because I've flattened it out, what I can do now is, in order to implement this explode function, I can find, now this is where the depth thing becomes handy. Let me go find where I put the string function for my numbers. I'm just going to print out the depth of the numbers. Yeah, so you can see this is starting to get a little harder to read, but you can see where this 6 is depth 2, this 5 is depth 3, this 4 is depth 4, and this 3 is depth 5, which is greater than 4. So when you have nested 4 times deep, then the number itself is going to be at depth 5. And you can see that this is carried over into here. When I have my numbers, I can see if any number is 5 levels deep, which means it's nested within 4 pairs. So all I have to do is traverse is go through this array from the left-hand side. And then as soon as I find a number that is nested 5 deep, I add the number to the previous one, I add the next number to the one after that, and then I take either one of these guys, I find its parent, and I replace it with the number 0. And that is the definition of what it means to explode a pair, which is described here. So that is the first part of reducing. You can see this reduce function is humongous. So let's take a quick look at what I mean by that. So I've expanded the tree into this iterator-like structure, this flat structure. I said the depth is greater than 4. Then that means we've found a number that is nested deep enough. If I is greater than 0, there are some edge cases that they talk about, like if you're at the edge, then nothing happens. So we'll just pretend we're not at the edge. We're not at the edge, so we take the previous number, I minus 1, adds the current number's value. So 4 becomes 7. And then the next one, 2 after that, you add the next value to the one that's 2 after that. So the 2 adds to the 1, and it becomes 3. And then this is that whole thing with working out the parent. So there's 2 halves of this because you have to figure out whether you're the left child or the right child of the parent. But in either case, the idea is the same. You find the parent. Then if you're the left child, then your parent's left gets replaced with a number. The number is 0. Otherwise, you do it to the right-hand side of the parent's parent. So I hope that makes sense. The specific code is a little bit tricky with which parent are you referring to and all that sort of thing. But the idea hopefully makes sense, right? And then I think they did this on purpose, is that once you've done an operation, you can reset and start again from the beginning of the whole number. Which means that I don't have to keep track of my indexes being right or wrong, or replacing things midway through. It's okay because you've replaced it, it's done, you start again from the beginning. So I go modified is true and I break with modified continue. So we don't do anything else. So that's the first operation. And the second operation is actually quite a lot easier. The idea is similar. You start with it's the split, which is anytime a number is greater than 10, you split it into a pair that's the number fitting inside it, like 10 becomes 5, 5, 11 becomes 5, 6, and so on. The rules are all in the problem description. So it's a similar thing. If we find a value that is greater than 10, then, or greater than or equal to 10, then we create a new pair. This pair, the left-hand side is going to be, you follow the rules, the number divided by 2, rounded down. Number on the right is the number divided by 2, rounded up, which is the same as number plus 1 divided by 2. You make sure your parent and your depth are all set correctly. And then, again, depending on whether the number was the left child or the right child, you set the appropriate one to this new pair. You set modified as true, which means that we keep doing this. See this loop up here? We keep reducing until there's nothing more to reduce. And you are done. So this reduce is in place, but I just return is a mutation on the original data structure, but I return it anyway just to make it a little bit easier to use. So just to kind of give an example of how this works, I can't do this one step at a time, but we're going to chuck the reduce into the add operation now. And we can just see with this example like they've given here. We'll have that, and we'll have here this. And we'll add the two together. Oh, and I'll get rid of all those depth printing just to make it a little bit easier to read. And you will see that the process of adding and reducing these two numbers, like it says, and you end up with the number that they want. And so I think this was the hardest part of this entire challenge, was coming up with a way to modify your data structure without, just to do that. And the way I did it was to flatten out the tree first, and that let me have a nice way to modify my data structure. It also helped that I was using pointers, because then I could actually go in and change things. Although I think with iterators, you can kind of do that anyway. So I think that was the crux of this challenge. And then after that, really the only other thing in here, I think, is that magnitude function. Which is not that scary compared to anything else we've done. Again, it's a recursive function, and they kind of describe it as a recursive function in here as well. Right? They said if you have 9, 1, it is 3 times the first left, 3 times left plus 2 times right. 3 times left plus 2 times right. And then when it's like this, it's 3 times the magnitude of the left plus 3 times the magnitude of the right. And so again, it's a recursive data structure. I have 2 variables, left and right, which is going to be the unmultiplied values. Do the same thing. If the left-hand side is a pair, then L is going to be the magnitude of the pair. And if it's a number, it's the magnitude of the value. On the right-hand side, do the same thing. So I have my magnitudes now, my left and right. So I return 3 times left plus 2 times right. And so given my homework assignment, here, we're going to have P is going to be new pair, the first number. And then for I equals 1 all the way to the end of data, we're going to add P and data I, which is going to reduce them all as well. We print P and we print the magnitude of P. Oops, that needs to be new pair as well. Made a mistake somewhere. Okay. I'm not sure where I might have made a mistake somewhere. So we're going to go back into my old code, just because this will demonstrate it actually running. Because here I have all the code in there in here as well. And so for that first part, I've added all the numbers together, and we get my kind of added sum and then the magnitude printed out, which was my answer, 4641. For the second half, they do mention that this is not a commutative operation, right? X plus y doesn't equal y plus x necessarily. And so for that second half, once you have the ability to add numbers, to reduce them, to get the magnitudes, that's all the hard work, right? Once you've done that, this part is straightforward. You just need to loop over every pair of numbers, add them together both ways, right? Data I to data j, and then here data j to data I. Because it's not commutative, we've got to try both. And then just do a max operation, which in Go, you have to do it yourself. So I just keep track of my max magnitude, and then I print out my max magnitude. And that's my second answer, 4624. So it's a really fun challenge, but at the same time, it's also not fun because of the code you have to write, which is kind of really confusing. In the end, I think it was a little on the hard side, but definitely very satisfying once you come up with a way to do it and then you are able to implement it. So if you still have to do this and you are going to give it a go, I wish you the best of luck. I hope this helps and gives you some ideas on how you might be able to implement it in your language of choice. Um, there's like what 2.5 hours to go until tonight's one. Again, I won't be able to do it live, unfortunately, but hopefully, it's not going to be as tricky as this one. So thank you for watching this video, and I hope to see you again for tomorrow's challenge.